Okay, welcome everyone. Maryam is going to be your speaker today. She's going to be talking about vertex operators for imaginary gl2 subalgebras in the monster Lie algebra. Feel free to start whenever you're ready.
Awesome. Thank you so much. Thank you for having me. And thank you for everyone for being here. So the title of my talk is kind of a mouthful. It's vertex operators for imaginary gl2 subalgebras in the monster Lie algebra. Hopefully I will explain what all of these different words mean. It is joint work with Darlene, Lisa, Liz, and Scott. Darlene, Lisa, Liz, and I met at the Banff International Research Station WinArt workshop, which was one of the most fun experiences I've had doing math ever, and one of the prettiest places I've also ever been to. So if you've never been to Banff, I recommend you try to go. This project is kind of a it started at Banff and now we're here. Here's the plan for my talk. So the outline, I am hoping to start by giving you the main results of the talk. So this section will be maybe there will be notation that I will not explain, and maybe it will be a little technical if you have no context of what I'm talking about, but don't worry, kind of treat this as a spoiler alert. I will give you more background in the second section. I like talks when people give you what they're going to talk about right away and not make you wait 40 minutes, right? So really treat this as a spoiler. And then I'll tell you the story of moonshine in the background, and this talk is about monster Lie algebra, and I will tell you how to construct it in kind of two different ways and why we're looking at it and all of that. And then the third section is more like, why are we working on this? What have we done so far? What's going to happen? So that's more of like motivational, high-level story section. And then I have a secret section that's over here, but you can't see it in the outline. My secret section is proof sketches. It's only if people want it and only if I have time. So if you look at a theorem and you're like, I don't know how you would prove that, can you tell me more? I will give you some proof sketches. Okay, so that's my plan, and I am going to begin by giving you the main results. Okay, so again, the paper and the talk is about the monster Lie algebra, which, recall, can be constructed in two equivalent ways. So it is both the quotient of the physical space of a vertex algebra, the vertex algebra being a tensor product of the Frankel-Påsky-Mermin moonshine module V natural, and a lattice vertex algebra. So it's a quotient of sort of a subspace of this vertex algebra by the radical of a natural bilinear form on it. And the other avatar of the monster Lie algebra is as a generalized Kac-Moody algebra, which we also call these Borcherds algebras. So I might switch between the two terms a lot during this talk. So the other avatar is that it is a generalized Kac-Moody algebra with a rank 2 root lattice, which I'm going to denote by L. So rank 2 means that this lattice is just Z plus Z, and it has a bilinear form on it. So the simple roots are 1, any integer, and the simple roots appear with multiplicity, and the multiplicity is C of n, which are the coefficients of the J function, the normalized adaptive modular invariant that I'm going to call the J function. Okay, so it's a lot of information, but the thing that I want you to remember from this slide is that the monster Lie algebra, it has two different avatars, one that is explicitly friends with the vertex algebra V natural, and one that is explicitly friends with the J function. So the vertex algebra avatar and the generalized Kac-Moody algebra avatar. I will also try to use these same colors kind of consistently. So like vertex algebra stuff will be in this pink purple thingy, and the Borcherds algebra stuff will be in teal blue kind of vibe. So you can keep track a little bit better. Okay, so this is what we know about the monster Lie algebra. What do we want to do? We want to understand the relationship between these two avatars better. especially in the light of the action of the monster group. So if you have heard the monstrous moonshine story before, then you might have this picture in your head of this triangle, that the monster group is related somehow to the J function, which is a modular form, and the coincidence of their relationship can be explained by the Frankel-Posky-Meerman moonshine module. So the monster group acts on this moonshine module, and its graded dimension is this J of Q. In fact, maybe this triangle is not the most accurate. Maybe instead of J of Q, I should write TG of Q for every G. So for G equals the identity, this TG of Q is just the J function, but I'm actually talking about the traces for every element. Now I'm going to say that I'm going to turn this triangle that you might have already had in your head to a pyramid, maybe more of a 3D picture, where I'm saying that the moonshine module is friends with the monster Lie algebra, but the vertex algebra avatar of the monster Lie algebra, and the traces that you get are friends with the generalized Kac-Moody algebra version of the monster Lie algebra. Okay, so what do we want to do? Well, we want to be able to connect this part, the monster group, to the generalized Kac-Moody algebra avatar, sort of, I want to say directly. Okay, I'm being vague, but this is the basic idea that we're going for. Something that we already know is that as a Borcherds algebra, the monster Lie algebra can be generated by subalgebras like isomorphic to GL2 that live inside the monster Lie algebra corresponding to the symbol roots. Okay, so this is known fact already. And our idea is that we want to write down explicitly elements of the vertex algebra that correspond in here to the generators of these GL2 subalgebras. In particular, that might make the action of the monster group on this more explicit. So again, when we get to the action of the monster group section, I will explain more what I'm talking about. But here's my first, here's our first theorem. So for this theorem, I'm going to fix an integer. I'm going to let C and D be, the 1, n and 1, -n, where remember 1, n is a simple root. So the C and D live in a canonical central extension of the lattice and so on. I'm going to let U and V be vectors in V natural, which satisfy some technical condition. And I'm going to define elements in the monster Lie algebra as its vertex algebra avatar, so as P1 over R. So remember, P1 was the physical space of the tensor product of V natural with lattice VOA. So V natural tensor V11. So the actual form of the elements doesn't matter. Right now, what matters right now is that we can define these 4 elements, and then the set En, Fn, Hn, and Zn is a basis for a GL2 subalgebra in M, corresponding to this N. Okay. Also, that's one theorem. And then the second theorem is that remember I said I pick vectors in V natural n+1, which satisfies some condition. We prove that for all positive integers, these vectors exist. So this theorem not only is an existence theorem, the premise, the hypotheses are actually satisfied. Okay, so that's my main theorems. Unless there are any questions, I'm gonna just get right into giving you some background for the story. There is a slide again, on which I will show these theorems again. So don't worry about missing anything yet. In section 3, these theorems will appear again. Questions, comments, worries? Okay, if not, so let's get into the story of moonshine and why the monster Lie algebra was first born. So the monster group, as we all know and love, is the largest of the sporadic simple groups. It has this order, which I'm not going to try to pronounce. Its smallest irreducible representations have the following dimensions: 1, 1, 9, 6, 8, 3, some other numbers. And John Mackay noticed that 19683 is pretty close to 19684, which actually you have also seen on these slides before. It's the coefficient, it's the q to the 1 coefficient of j of tau, the normalized uptick invariant, so on. So Q forever in this talk is always going to be e to the 2 pi I tau, where tau is a complex number with positive imaginary part. And the coefficient 19684 is very close to the smallest non-trivial irreducible, the dimension of the smallest non-trivial irreducible representation of the monster. So maybe this is a coincidence, maybe not. John Thomson noticed that actually more than this is true. Not only is the first coefficient of j can be written as like a specific sum of dimensions of irreducible representations. In fact, more coefficients of j can be written like this as well. And I don't have this on a slide, but actually you can do this with other modular forms and other columns of the character table of the monster. So similar relationships exist. But this is sort of enough evidence for John Thomson to conjecture that there's something going on. So he conjectured that there is a infinite dimensional vertex operator infinite dimensional monster module whose graded dimension is j of tau. And the final moonshine conjectures are these, which I've kind of combined everything that everybody said in one. But here's the conjecture. So there exists an infinite dimensional monster module, V, whose graded dimension is j of q. And for each g and g, the graded trace is a special modular form. It's a normalized hot module for a blah, blah, blah. But basically, Conway and Norton gave us an explicit list of these modular forms. There are 194 conjugacy classes of the monster. So they gave 194, modular forms, and they said it's these ones. So this is the conjecture. And in order to prove this conjecture, Frenkel, Pauski, and Merriman constructed V natural, which is an infinite dimensional graded vertex operator algebra whose graded dimension is j of q, just like in the conjecture, and whose automorphism group is the monster. So it satisfies a lot of these things. Also, they computed these traces for V natural for like a large subgroup of the monster, and they showed that those traces are actually, again, the modular forms that Conway and Norton had written down. We didn't have all of these traces though, because it's not an easy task to write down these traces. The construction of V natural is very complicated. The reference I have is a book, not a paper. So it's a really complicated construction. So it's not easy to explicitly write down these TG of Q. So we maybe needed an indirect approach for the other elements. And the other elements is where Borcherds came in, and he constructed the monster Lie algebra in order to do this. And he won a Fields Medal for it. So it's kind of a big deal. So roughly speaking, this is what Borcherds thought to do. He observed that this well-known product sum identity for the J function. So this is an identity that was known to number theorists already for a while, right? And he looked at this and he was like, maybe this kind of looks like the denominator formula of a Kac-Moody algebra. Okay, does it? Well, okay, if I let alpha, which are positive roots in this formula, if I let them be m comma n, and I let multiplicity of alpha be cmn, and I replace things appropriately, maybe I can make this side like which side is this left? The left-hand side look like the left-hand side. However, the right-hand side will kind of never look like the right-hand side because this one is actually a finite sum and this is an infinite sum. So if I just was looking at a Kac-Moody algebra, and I'm making the sound more vague than it is actually, there is a standard procedure. If you have a denominator formula and it came from a Kac-Moody algebra, there's a standard theorem of Serre that you can apply to try to write down what the Kac-Moody algebra was. But if you do it with this J function identity, you assume it came as has a denominator formula, then you run into this problem. It doesn't come from a normal Kac-Moody algebra. So what Borcherds did was he very conveniently was like, let's create a new class of Kac-Moody algebras. Well, he called them generalized Kac-Moody algebras. I will sometimes call them Borcherds algebras. And the difference, as he said, between a Kac-Moody algebra, the main difference is that you're now allowed to have imaginary simple roots. So by imaginary, I mean that the norm can be negative. So in a normal Kac-Moody algebra, your roots can be real or imaginary, but your simple roots have to be only real. But in a generalized Kac-Moody algebra, you're allowed to have imaginary simple roots. So he constructed a generalized Kac-Moody algebra, one of the first examples of it, and it was the monster Lie algebra. And I want to take a detour now and tell you about the monster Lie algebra as a generalized Kac-Moody algebra. So you can write down the monster Lie algebra as G of A mod Z. Where G of A is the Lie algebra that you get from this generalized Cartan matrix. I want to point out that Borcherds didn't actually write down a Cartan matrix. His description of it was a little different, but you can show that it's this is a description you can use, and we will use this one because it's convenient for us. Anyway, so G of A is the Lie algebra given by this generalized Cartan matrix, and Z is the center of this G of A. This is an infinite dimensional matrix, but it is a block matrix where the block sizes are given by the Fourier coefficients of the J function. Okay, so that's one way of getting the monster Lie algebra. Some facts to know about it is that the root lattice is the lattice L, as we mentioned earlier, which is Z plus Z with the bilinear form given by this matrix. The simple roots are 1, n, each with multiplicity C of n, and the denominator formula is exactly the J function identity. So Borcherds has constructed a Lie algebra, which is explicitly friends with the J function. And if now, again, remember what he's trying to do is like trying to connect the J function with the monster group, or finish proving that like the conjecture, the monster dimension conjectures work. So now we need a different way of connecting the same Lie algebra to the vertex algebra V natural, which is the vertex algebra construction. So he separately constructed the monster Lie algebra as a quotient of the physical space of the vertex algebra V natural tensor V11, where V natural is again the Frenkel-Pasky-Merman monster module, and V11 is a lattice vertex algebra, again the same lattice throughout L. Okay. I should tell you what a vertex algebra is. So remember that an algebra is a vector space with a multiplication defined on it. And a vertex algebra is, in very simple, vague words, I'm not going to give you a definition, but in very simple, vague words, it is a vector space with an infinite number of multiplications defined on it. We're going to write them as U and V. So instead of writing UV for a single multiplication, we're going to write U and V. And you want them to satisfy some axioms, compatibility type axioms. All of the vertex algebras we encounter are going to have a special conformal vector. I am also not going to define what a conformal vector is, but I'm going to tell you that we will write Ln to be the operator omega n plus 1. And for eigenvectors of L0, I am going to call the eigenvalue to be the weight. And I'm going to define a primary vector to be such that Ln of V is 0 for all positive n. Okay, so why am I defining all these things? Well, I'm defining them because I want to tell you what the physical space of the vertex algebra is. So I'm going to call the space of primary vectors of weight 1 to be the physical space P1 of this vertex algebra. If I let V to be the tensor product, V natural tensor VL, then the monster Lie algebra is the quotient P1 over R with this Lie bracket. where R is the radical of a natural symmetric invariant bilinear form 1B. Okay, so again, the theme of this talk kind of is that the monster Lie algebra has two avatars. One of them is friends with the J function, and the other one is friends with the with V natural. This is the other one. And I want to point out that if you look at the monster Lie algebra from this lens, if you consider it as P1 over R, it is actually very, very easy to like see what the action of the monster group is on this Lie algebra. It acts trivially on the lattice VOA, and it acts by VOA automorphisms on V natural. Remember that the monster group is the automorphism. It's the automorphism group of V natural. Okay. So how did where did Borcherds go from here? He used the no-ghost theorem from string theory to prove that the two avatars are the same. And how did this help him? Well, he can use the fact that the monster Lie algebra is a Borcherds Lie algebra to now write down the twisted denominator formulas for V natural. So he's using this connection to write down this twisted denominator formula. This doesn't look a lot like the J function identity in the way that it's written, but in fact it is exactly that if you replace G with the identity element. And it's a strong enough connection. It gives you strong enough relations between the coefficients of these TGPs that you can determine them from their first few Fourier coefficients. Also, the list that Conway Norton gave remember I said they're normalized hot modules, and I never explained what those are, but one of the properties of like normalized hot modules of genus zero subgroups or these very special modular forms is this thing that I think it's called replicability, is that you also have these recursion relations between the coefficients. So actually the problem at this point boils down to just comparing the first few coefficients of the modular forms, and you can do that numerically, and that finishes Borcherds proof. Okay, so that's what Borcherds did. So what are we doing? Why are we interested in this to begin with? Well, the big part of our motivation is that this isomorphism between the monster Lie algebra as a Borcherds algebra and the monster Lie algebra as a quotient of a vertex algebra is non-constructive. And it is not easy to extract meaningful information about the monster on the generators of the generalized Katz-Moody algebra M, right? So we want to kind of parse out this action a little bit more. Okay, the other big part, I had forgotten what my next slide was, so that was that pause. The other big motivation for us is this theorem by Jurisic-Lebowski-Wilson, where they describe the gl2 subalgebra corresponding to the real simple root. There's only one real simple root, and you can actually write down I want to say an analog to our theorem, but our theorem came later. So our theorem is an analog to this theorem. You can write down these elements E, F, H, and C, which span a copy of GL2. And if you write them down this way, then it's actually pretty easy to see that the monster group acts trivially on this GL2 subalgebra. Why is it easy to see? Because remember, these E, H, F, and Z in the case of Jurisic-Lebowski-Wilson, the contribution from the V natural part is just the vacuum element, and the monster group acts trivially on the vertex VL part anyway. So it actually acts trivially on this entire GL2 subalgebra. So again, if you write things in this way as elements of P1 over R, then it's easy to see the action of the monster group on it. So now my promised slide with our theorems is back. This is the same slide I showed earlier, but I'm going to pause here for a while now because I feel like before maybe I hadn't said enough things to be able to absorb this fully. But notice that this is an analog of the Jurisic-Lebowski-Wilson thing. We don't have vacuum vectors anymore, so our action is going to be a little bit more complicated, but hopefully more explicit. And again, we can prove that such primary vectors exist. So there are always things that satisfy the hypotheses of this theorem. Okay. We also prove that if I fix an element of the
sorry,
yes.
Can I ask a question? And
yes,
could you
of
go
course.
back one slide? So this
Yes.
n+1 that shows up under the
Yes.
Munchen module is degree n+1,
Yeah, that's homogeneous weight n+1. Yes.
and you can show that there's always such primary vectors at all degrees.
Yes.
Very cool.
Yes,
Thank you.
in all degrees. Yes. Right. Yeah. So yes. So primary vectors of every weight greater than 0 exist, basically. So yes. Yeah, it's okay. I also, while I was like looking at my slides earlier today, I was noticing that like there's so many n+1s. This is a mode of the Vertex algebra. This en is just an index saying that this is indexed by n. So like it's confusing. So very fair question. But it's yeah. Okay, so what can we say about the action? I've like set up this story saying that we might know things about the action. Here's what we can say about the action. So if I fix little g and m, and I take this set ENFN for a fixed n and a fixed g, I take the set ENFN, HN, and ZN, and I act by little g on them. Then I have these new elements. The action of G only affects this part, and we can prove that these new elements are still primary vectors, still satisfy the hypotheses of theorem 1, and so we get a new copy of the GL2. We get a new copy of the GL2, and we want to say our conjecture is that this action is non-trivial. I'm calling it a conjecture, and then I'm writing a theorem in kind of quotes. What is this the theorem? I think the current status is that we can compute this. We can check this numerically for small n. We can prove this for asymptotically large n, and we believe it is true for all n, but we don't know how to do the middle things yet. So the action possibly might be non-trivial. Okay. Okay, I want to give you a quick summary of this because I feel like I've said a lot of words. This is a complicated story. But again, remember the triangle that I made earlier? This is the triangle. So this is V natural, this is the monster group, and this is the traces of V natural, the graded traces. And instead of just saying that this is a triangle, now I've added the monster Lie algebra in there. V natural is friends with the monster Lie algebra if you look at the monster Lie algebra as the physical space modded out by the radical of a bilinear form. The traces are kind of friends with the monster Lie algebra if you look at it as a generalized Kac-Moody algebra. And the monster Lie algebra happens to be the same thing by the no-goes theorem. And our hope is to like bypass this whole process and like kind of look at the monster Lie algebra as a generalized Kac-Moody algebra. Because remember, generalized Borcherds algebra or generalized Kac-Moody algebra was first constructed sort of to solve this problem, right? To fit into the story. But it is now interesting on its own. Like a generalized Kac-Moody algebra is an interesting object on its own. And in fact,
Maryam,
yes,
I just wanted to say, could you just
yes.
go back to the previous slide?
Yeah.
I don't know if we think that we've got this line between the monster Lie algebra and the graded traces.
We think that we have the line.
I don't know if we have a line between those two. Your line between NT and T natural G of Q.
Yeah, I think that's a good point. I think in my earlier picture, I made this line like broken. Like we're trying to make this line, and it comes.
That line, the bottom line is good. The diagonal line between the monster Lie algebra and the graded traces.
You don't like this?
That's a question mark.
Really? Huh?
I mean, we don't have a way to go from the Lie algebra to these traces. I mean, this is one of the things we're trying to do. But there should be maybe a question mark there.
Okay. Yes. Okay. I guess, let's see. Okay, maybe this is a question mark. I think maybe if I write J of Q, are you happier with that? Is that okay?
J of Q is definitely encoded in the monster Lie algebra. So that yes. That
Yeah. Okay. Okay, that makes you happier. Okay, so that's maybe what I want to write then. I want to make this J of Q. Okay, very good. Thank you. So where was I? Yes. So I want to say, okay, so this was the pitch that I was making for a second. So I was trying to say that generalized Casimodi algebras like are objects that maybe exist because of the story, but they are now objects that are interesting on its own. And if you have a Lie algebra, then you should have a Lie group, and you should be able to say things about that. And Lisa, Liz, and Scott have a construction of a Lie group analog for this, for the monster Lie algebra. And what we have done is we want to know. Sorry, yes. Our elements that we have constructed give you images and images in M that can be used to just generate a subgroup of this Lie group analog. Okay, so maybe interesting in this regard is what I would like to say. Other future things that we might want to be able to do. So first, we have constructed a gl2 subalgebra for each primary vector, right? Because like all of the vectors that I'm dealing with are primary, but primary vectors don't span all of V natural. So in fact, I don't have like the full picture for the monster Lie algebra. So something that we would like to be able to prove is that if you take the set of generators for our gl2 subalgebras and you take the ones given by JLW, which are for the real real simple root, and you take a union of this set, well, it won't be an entire set of Serre-Chevalier generators for the monster Lie algebra, but can we prove that it extends to one? So this is the same as like in a vector space, if I give you a linearly independent set, maybe it's not a basis, but you can usually prove that it extends to a basis, right? And don't want to misquote Liz, but I think that Liz thinks that we can do this kind of in a standard way. It's like the Graham-Schmidt, but on steroids, I would say. So that's kind of our motivation there. And then we are kind of in the process of exploring what to do with the non-primary things. So we have this conjectural table. So primary vectors live inside of V natural n+1, and their dimensions are, so we have for Vn+1, we have a way of decomposing Vn+1 into irreducible representations. But can we figure out which of those are in the primary ones and which of those are not? So what is the decomposition of the non-primary vectors in terms of irreducible representations? And then can we use that somehow to say things about non-primary vectors and gl2 subalgebras generated by those? Okay, I think that is all I have to say if I never get into proof sketches. So I'm going to pause here for questions. And if people do want to see some proof sketches, I'm very happy to show them to you.
Thank you so much, Maryam.
Thank you.
Any
yeah,
questions
I think
for Maryam? Sorry.
Yeah.
I'll start with a question. So
yes.
Can you say a little more about the non-primary vectors? What is Pn+1 in this slide?
Okay, so Pn+1 is the submodule of Vn+1 that consists of primary vectors. So let me see if I can write things down. Yes. So this lives inside of Vn+1, and Pn+1 is primary vectors of weight n+1. Remember, primary is L0 gives you n+1, and ln will annihilate it. So it's things that are annihilated by ln, where n is greater than 1. So that's what the primary vectors are. And why am I talking about primary vectors? Well, in the theorem that I have stated, I've always said, let u and v be primary vectors and this v natural n plus 1, and then I can construct this. And in fact, the content of theorem 2 is that there are primary vectors in v natural, full stop. The rest of this, that you can actually pick ones that do this, is the sort of trivial part. You can pick u and v to be equal, which doesn't give you exactly this. It gives you a scalar multiple of this, and then you can, find the scalar multiple of u. And so the content is that there are primary vectors, and then actually for each primary vector, fixed n, I've given you a way of like constructing this. But primary vector, there are clearly vectors in Vn plus 1 that are not primary. So what do we do with those? And maybe there is some like, we don't know yet. This is the vague part of the talk where we are still figuring out what conjectures.
Maryam, for the table, maybe just point out that that Pn plus 1 is an M submodule of Vn.
Yes, very good.
So it's actually, it's a theorem, but it is an M submodule.
Yes.
Which is kind of what allows this table to
exist. Yes. Yeah.
Thank you. Any other questions for Maryam?
Yeah, can I just want to make sure that I understand. So if you pick any two primary vectors, you have a construction that gives you this gl2 submodule.
If I pick two, so if I pick two primary vectors that satisfy this, okay, wait, how is this not working?
You fix a weight n plus 1.
So you fix a weight, yes. So you fix a weight and you want the primary vectors to satisfy this. This is a vertex operator algebra, condition. So u2n plus 1, so 2n plus 1 mode on V should give you this multiple. Okay, so it looks like a weird condition, but now I'm saying that in fact, if you give me just one primary vector, I can always find a V that will do this.
Yeah, I mean, this seems like this is some kind of bilinear form in this space.
Yes.
The form is non-degenerate because the VOA is simple, so you should be able to
exactly.
Okay, so this is just, you choose something which is dual to, you pick a U, you pick something dual to it, that always exists. From those you get a, okay, so and there's no uniqueness for this. You always get a GL2 for any U and any V which is dual to it.
There's no, yes, exactly. So there's, we're not making any claims about like, if you give me a U, this is not the only V that will work necessarily. Yeah.
Okay. And these GL2s, how do you compare them? If you vary the space, let's say you fix U and then you vary V and you do this construction, what is the relationship between the different GL2s that you find?
Okay, that's a good question. Let's see.
They're all isomorphic. And some of them might be in the same orbit of the monster group, actually. We don't know.
That was the next question. So it seems like the monster preserves this primary space, so it moves around these different.
Yeah, exactly.
Yes.
Yes. That's for the decomposition. Okay,
yeah. So when I say the action is, sorry, I'm interrupting you, but when I say that the action is non-trivial, I don't mean that it has no fixed points. I generally mean non-trivial as a monster action. So it doesn't mean that given a singular gl2 subalgebra, it can't be fixed by the entire monster group. It could be.
Okay.
Yeah.
So one of the objectives here is that we don't actually know what the monster finite simple group action is. For us, it's a black box given to us by the no-goes theorem. And what we're trying to do is pull that action down from V natural. It was described by Frenkel, Lepowski, and Merman. We want to pull it down to the monster Lie algebra and actually see it concretely. But for the moment, it's just a black box. And so also one of the next things we'd like to do is go back to what Frenkel, Lepowski, and Merman did and view the monster finite simple group as a group generated by a centralizer of an involution plus another involution. Because from that, in that framework, they computed they did very detailed computations of the orbits of the monster on V natural. And we want to try to pull down that entire structure on the monster Lie algebra. So right now we can't answer your question, Andrew, but this is sort of the first step that will show us what to do.
Can I ask another question? Maybe this is related. So I don't work in this area exactly, so it's all these may not be good questions, but I'm curious about something. So this construction gives you a very small Lie subalgebra of the monster Lie algebra. GL2 is a sort of very small subalgebra. If you take these vectors, this U and V, this is a special. They will generate some subalgebra of the monster VOA.
Oh no, they generate the monster Lie algebra. These GL2s. So we're constructing.
No, I just pick one of them. Just
a fixed one. Yep.
Yeah, so you get something small, and then the corresponding vertex algebra in the monster VOA that's generated by just U and V. What does that look like? So that is.
It's just a subspace primary one. You
will get you'll get a GL2 Lie algebra right inside of V. You'll get a GL2.
The weight, the conformal weight is n+1. So you don't have a. It's not an affine Lie. It's something. I mean, I don't know what it is. Maybe it's an extension of a Soro by 2. So
that's actually really nice. That's a really nice question. Actually, I don't know the answer. You say that the reason the GL2s are significant on the level of the monster Lie algebra is because it's a generalized Kac-Moody algebra. When you look at that Cartan matrix that Maryam wrote down, for any Lie algebra, for the diagonal entries, you've got an SL2 triple.
Yeah.
But because the Cartan subalgebra is two-dimensional, these extend naturally to a GL2 quadruple. And so that's actually the GL2s that we're computing here. It's exactly those. So a family of those from the diagonal entries will generate the entire monster Lie algebra. But what their images are upstairs, it's going to be something in the physical space. That's a very good question. I don't know.
Okay.
Anyway, yeah, thank you. Yeah, very interesting.
Yeah.
Maryam, do you want to use maybe the last 10 minutes we have to tell us a little bit about the proof sketches?
Yes, wonderful. Okay, so proof sketches. So reminding you what theorem 1 was. So this is the theorem. I'm going to try to tell you how to go about doing something like this. So again, we are trying to find primary vectors that satisfy yes, so we're trying to find primary vectors of weight 1. So we're trying to find vectors in P1, right? Yeah, yes. So I'm trying to find vectors in P1 mod R. So I'm actually trying to find vectors in P1 whose projection under this quotient map generates a copy of GL2, right? And so this is what we're going to use. The main lemma is going to be that if I take something in V natural that is primary in V natural, so now I'm going to use the word primary, and remember that V natural has a conformal vector. VL actually happens to have a conformal vector, even though it's not a vertex operator algebra, but it has a conformal vector. So when I say primary in V natural, I mean, it satisfies the definition for the Ln in V natural. So if I take a vector that is primary of weight n in V natural, and I tensor it with a vector that is primary of weight m in V natural, then we can prove that x tensor y is also primary, and the weights just add. So that's pretty good. That means that maybe if we find something strategic in VL, and something strategic and be natural such that their weights add up to 1, then we're good. So first, let's try to find something strategic in VL. So VL, again, I'm not going to describe the entire lattice VOA construction, but it's a tensor product of the symmetric algebra for on the negative part of the standard Heisenberg algebra, and with the twisted group algebra of the lattice. And here's the next lemma, that if I take the part in S to be just the vacuum, then those vectors are primary. So in particular, if I take C to be m comma n, where m comma n lives in the lattice, right? So then one tensor iota C is primary and its weight is minus m times n. Okay, so that's why it makes sense to pick. So remember in our theorem, we pick C to be 1 comma n. So its weight turns out to be minus n. And then we need a vector in V natural, which has weight n plus 1 to give you an added weight 1. So we're going to take, and I'm suppressing this one tensor now. This should be like 3 tensor products where the middle one is always 1. So we're suppressing it. So I'm taking something U and V, which are primary of weight n plus 1 in V natural. And I'm taking C's and D's to be 1 comma n and 1 comma minus n. Then E and F are, then if I define them this way, then they're primary of weight 1. And then you do a vertex algebra computation. You try to compute this. Remember that the Lie bracket is given by X. So let me write it down. Remember that the Lie bracket for X plus R, Y plus R, where this lives in P1 over R, is given by X0, Y plus R, where X0, Y now means that the 0th mode of X and so on. So you do this computation, you compute what X plus R, what E comma F looks like, and you get this element. And then you take this element, you say, let's say that is H, right? And then you take the H comma E, so you get minus 2 times E times something else, which the something else, if you force the condition that it is just a vacuum, then you'll get, so I'm making this sound again like glibber than it is, but basically this condition on the primary vectors falls out of the proof. So again, we want primary vectors, we want them to be weight n plus 1, and we want them to satisfy this condition. So that's the idea behind the proof of theorem 1. Mostly the content is doing this vertex algebra computation. And for theorem 2, I want to find primary vectors in V natural that satisfy this condition, which I think Andrew already pointed out how you would do it. If you knew that there is a primary vector to begin with, this is just something about the bilinear form. So how do you know that there is a primary vector to begin with? The graded dimension of the space of primary vectors is actually given by this generating series, which is very close to a modular form. It's not exactly modular form, but it's J of Q times 8 of Q times some power of Q. And we can prove using properties of the J function and 8 of Q, which remember is Q to the 1 over 24. It's this product, 1 minus Q to the N. So we can use properties of J of Q and 8 of Q to show that the coefficients of Q to the N in this series are actually all non-zero, or positive, I guess. Yes, positive, because these are dimensions for all n greater than 1. So that would prove that like primary vectors exist. And now once you have a primary vector, I want to find ones that give me this. How do I do that? Well, I use the bilinear form. And the bilinear form is non-degenerate and positive definite. And so you can, for any non-zero u, you can you have that u comma u is some non-zero multiple of the vacuum vector. And then you can take v to be the appropriate multiple. So then this thing turns out to be the right thing. So that's my very quick proof sketch for the two theorems. Okay, now I'm actually done.
Wonderful.
If there are any questions, please let me know.
Thank you so much.
Thank you.
Any final questions for Maryam?
Maryam, your summaries are so nice. We should use them to rewrite the paper.
Oh, thank you. Thank you. I like diagrams. I've spent okay. I will not tell you how much time